Okay, so let's start today's lecture. Okay, so let's start today's lecture. Okay, so last time we have been talking about the real, the two by two systems of linear equations. Okay, so what we have covered last lecture is about such equation x dot is equal to a of x, where x of 0 is given by some x0. So we talked about this, and in that case, we have set our A to be the matrix like A, B, C, D is a 2 by 2 matrix, and x of t has the components x1 of t as well as x2 of t, right? So that's what we have been talking about last lecture. And then we say that general steps. Okay, so general steps. Okay, so the general steps is going to set like the determinant of a minus the ri is going to 0, and then that gives you the some r1 and r2 for each of them. So r1 is going to give you like the first eigenvector, r2 is going to give you like the second eigenvector, and then the solution. Okay, so the solution. So based on the assumption that r1 and r2 are both real numbers and they are not equal to each other, the solution is going to give you like x of, so the general solution, right? So the general solution, so let me say steps. Okay, so the general solution is going to look like the x of t is c1 e to the power of r1 of t of x1 plus c2 e to the power of r2 of t of x2. So that's going to give you the solution. Okay, so that's kind of only covers the situation where you have a so-called real distinct root case. Okay, so it only covers the like the standard situation where you are going to have the real distinct root case, but it's a very important case that happens very often. So what actually happens for other cases, right? So what are the other cases? Well, there are some other cases, right? So what are the other cases? Well, the first case is that it might happen that both of the roots are real and they are just the same, right? So R1 is equal to R2. And it is also possible that R1 is equal to, lambda plus I times mu, and R2 is equal to lambda minus I times mu. They are complex and conjugate. Right? So they are complex and conjugate. So that's kind of two possibilities, like real repeated root case and complex conjugate root case, right? So they're going to have all these scenarios. Okay, so now once you have that, we have to kind of alter, right? So we kind of have to change this formula for the general solution accordingly. Okay, so today's lecture we're going to talk about the real repeated root case. Okay, so today's lecture, we're going to talk about the real repeated root case. Okay, so real repeated root case. So that means you consider the solution equation x prime is equal to a log x with a 2 by 2 matrix A. You have two eigenvalues and two eigenvectors. We discussed the case of R1 not equal to R2, they are real. And what happens if both the roots are repeated eigenvalues and they are the same? So in that case, you can see that what is going to happen is that you're going to have Ax is equal to R of x, but the eigenvalues, okay, so let's say determinant of A minus the Ri is equal to 0 is going to give you two solutions that are the same. They're both real, right? So that means corresponding to the root R, okay, so corresponding, so corresponding to eigenvalue R, we find, right? So we find like A of the, let's say, so A of the x1, is equal to R of the x1. So you're going to find an eigenvector, right? So as we did before, you can just solve this linear system of equations. You find a relation between the components of the first and second components of x1. You're going to find a solution. Okay, so that you find a solution. But then for R2 equal to R, we lack solutions. We lack eigenvectors. why we lack eigenvector? Because the second eigenvalue is as the first one. Is they are the same, so you're going to arrive at same eigenvector that you lack a new eigenvector. Is that good, family? So we're going to kind of produce a new eigenvector. So what we should do? So let's say what we should do. Okay, so let's say what we should do. Right, so what are we going to do? Well, remember, in a case when you have real repeated roots for the higher order equations, we've been using the golden principle, right? So there's a golden principle. Okay, so golden principle means that you insert t's, right? So you insert t's. So that kind of it might happen, right? So basically, it means that, for example, for the first eigenvector, right? So like what you see before, your fundamental solution is going to be like e power r1 of t, right? So in a vector case, you're going to have like x1. Okay, so you're going to have like the first part of the solution, x1 of t is going to be e power rt of x1. So that means it looks like the x2 of t, according to the golden principle, you just insert t is t power rt of x1, then looks like you should be done, right? So it looks like you're fine with this scenario. Okay, so with this scenario, but in fact you are going to kind of it's kind of I mean it kind of misses something. Okay, so let me use the common vector x. Okay, so to denote the first eigenvector. Okay, so that's going to be the x. Okay, x is the first eigenvector. So is the solution just a combination of e power rt of x and t power rt of x? Well, the answer is like not exactly, but very close. Okay, so what happened here is that okay, so let's say procedure. Okay, so what happened here is that you have to follow the following procedure. Okay, so you have to follow the following procedure. So we look at a, okay, so of x is equal to r of x. For the common real root, you're looking for the eigenvector of this equation. A of x is r of x. We're going to kind of view this equation as a minus the r times I multiplied by the x is equal to 0. Okay, so it's equal to the 0 vector. Here, 0 with an arrow on it means the 0 vector. Okay, so, and this is actually automatically true because the r vector by vector x is r like the identity multiplied by x. You move the r identity to the left, and you get this. Okay, so you're going to. Now we're going to kind of, if you kind of look at this equation, okay, so this equation can actually be viewed as a black box. Okay, so this equation can actually be viewed as a black box in the sense that let's say 0 is the input. Okay, so 0 is the input, and then the x is the output. And how do you find the input and output? You set 0 as the input. Then, according to the equation, a minus ri of x is equal to 0. You're going to solve for the x. So x is the output. Is that good, family? Okay, so now we're going to continue this procedure. So if you continue this procedure, it means that you can use the first output, right? So you use the output for the first equation, x as the new input. So you're going to look for a minus ri multiplied by y is equal to x. So what actually happened here is that the output of the first equation now becomes the input of the second equation, and then you produce another output. So basically it means that you're going to continue this process. Basically you said a minus ri of y, right? So you're solving for some y, right? So you're going to look for a minus of y is equal to x. You kind of find another vector y. So that's going to be the scenario. Is a good family? Okay, so that's going to be scenario. And moreover, if you kind of set, okay, so if you kind of use the first equation, you're going to kind of immediately find that a minus ri squared multiplied by y is nothing but a minus ri and multiplied by x, because a minus ri, you take one factor out, that's going to be the x, and this x is going to be 0. So y is actually a solution of another equation, a minus ri squared y is equal to 0. Is that good, family? Okay, so this is only a remark. Okay, so this is only a remark that this is also true. So once you have all this, okay, so once you have all this, you kind of find another vector y. Is that good for okay? You kind of find another vector y. So basically, we have found one vector x, which is the original eigenvector. But based on this eigenvector, use this input-output analysis, you find another vector y. Okay, so there are two vectors x and y. And then for the general solution, okay, so the general solution actually is kind of subject to the following formula. We're going to say that x of t is equal to e, okay, c1 e power rt of x. This is as before, and then it's going to be c2. Okay, so we're going to use t e power rt of x. This is like what we did in the golden principle, right? So this is what we did in the golden principle that we have just mentioned. Okay, so but then you have to kind of correct the golden principle by another e power rt multiplied by the new vector y. Is a good family. Okay, so the new vector y was found by using this input-output analysis. As we just mentioned, you have to kind of put the matrix A minus Ri multiplied by y is equal to the x, which is the output of the first equation. You solve for the new y, and this y has to enter this solution as this formula. Is that good family? Okay, so this is the general formula. Okay, so this is the general formula for the real repeated root case. Is that good? Okay, so let me remind you, there is a vector y, there is a vector x. Okay, so the review of the procedure. Okay, so of the procedure is as follows. Okay, so the for procedure is as follows. You have x dot is equal to a of x, and you're going to solve for determinant of a minus the ri is going to 0. It gives you ry is equal to r2 is equal to r, so that you're going to look for the eigenvector ax is equal to r of x. But then you're going to look for another equation a minus ri multiplied by y is going to be equal to your first vector that you found into the x, and you find both x and y. You use this formula that's going to give you a general solution. So this is the case for the real repeated roots. Is that good for everybody? Okay, so now let us practice several problems to just get familiar with this procedure. Okay, so here let's first look at this problem. Okay, so this problem is let's look at this problem. Okay, so this is just to find a general solution. So we don't have to quite worry about particular solutions, right? So just to work with this general solution. Okay, so let's say how to work with this equation. Right, so we want to work with this equation. So how do we work with this equation? Well, of course, you're going to set x to be equal to x1 and x2 of t. They are functions of t, right? So the matrix A is actually given by 1 minus 1, 1, and 3. So then you're going to say that I will look for determinant of A minus Ri. So that's going to be the determinant of 1 minus R minus 1, 1, and 3 minus R. So that's going to be 1 minus R multiplied by 3 minus R plus 1. Is a good family. Okay, so this is going to be like the R square. Okay, so let's say 3 minus the 4 times R plus the 4. So that's going to be R minus 2 square. If you set this to be 0, you're going to see that Ry is equal to R2 is equal to R is equal to 2. So the common real eigenvalue is going to be 2. Is that good, everybody? Okay, so then you're going to look for eigenvectors. So the first eigenvector is definitely according to the equation ax equal to 2 of x. So that's going to give you like 1 minus 1, 1, and 3. Okay, so that's the matrix A multiplied by x1, x2 is equal to 2 times the x1 and x2. So that's a simple linear system of equations. X1 minus x2 is equal to 2 times x1, and x1 plus 3 times x2 is equal to 2 times x2. So that's going to give you, the first equation is going to give you like the x, okay, so x2, let's say, okay, so the first equation is going to give you like x1 is equal to minus x2, because you move this x1 to the right, you get this equation. Now the second equation is going to tell you that x1 plus x2 is 0, which is the same thing as the first equation. So that means you can just take the vector x to be 1 and minus 1. Right? Remember, we like ones, we like zeros, we like integers, but we have to satisfy this equation. And it is good to see that both equations give you the same answer. So that's going to you just pick 1 minus 1. So the first vector is found. But the problem is about repeated roots, right? So the problem is about repeated roots. So you have to kind of, according to our general schedule, you have to find the equation for the second root. Is that good for everybody? Okay, so that means you're going to look for a minus the ri. R is the common real value, eigenvalue, so that's 2. Right? The common real value into eigenvalue is 2. So a minus ri multiplied by y is equal to the x. Is that good for everybody? Okay, so therefore, you have to kind of first look for the matrix a minus 2i. So what is the a minus 2i? Well, a is 1 minus 1, 1, and 3. So minus 2i is 1, 1, 0, 0. So that's going to be like 1 minus 2 is minus 1, and then 1 minus 0 is, so that's 1, right? So you're going to have a 1, and 3 minus 2 is 1. So you're going to have this. And therefore, you're going to look for minus 1, 1, and 1, multiplied by the vector y1 and y2 is equal to the x, right? So what is the x? X is equal to like the 1 minus 1. So that's 1 minus 1. So you get system of linear equation minus y1 minus the y2 is equal to 1, and y1 plus y2 is equal to minus 1. Of course, again, these two equations are kind of equivalent. You can just work with one of them. So you're going to set y to be, okay, so that means y1 minus y2 is equal to 1. So you can set y1 to be minus 1. You set y2 to be 0. That's going to be a solution. You just need to find one solution that satisfies this equation. Is that good for everybody? Okay, so according to our procedure, the next step is to get the general solution. Okay, so the general solution. So the general solution is going to be x of t, right? So I mean this formula. Okay, so this formula here is something that you have to remember. Okay, so this formula here is something that you have to remember before you enter the exams. Okay, so we do not give you this formula on the exam, but you have to memorize it by yourself. However, there are tips to memorize this formula because it's easy to see that C1 e to the power RT of x plus C2 t times e to the power RT of x is like the system, I mean, it's like the higher order equation case, but just work with a new vector x. I mean, this is the fundamental solution. So you're going to use the golden principle, you multiply by t. So this is very easy to memorize. However, you must also realize that in a vector system vector case, you have to add another vector without the golden principle. So basically, you change either both the golden principle as well as the vector. Okay, so the golden principle was covered before. You just enter a t, but as the vector, you have to find a new vector y that satisfies the equation a minus ri y is equal to x. You put a vector there, you're going to get a solution. Is that good? Okay, so that's going to give you a very simple answer to this question. It's going to be C1 e to the power of 2t multiplied by the vector x that we just found is 1 minus 1 plus C2 t times e to the power of 2t plus the vector 1 minus 1 that we just found. And then it's going to be e to the power of 2t multiplied by minus 1, 0, which is the new vector that you find. Is that good for everybody? Okay, so that's the general solution to the original problem. Okay, so to the original problem. So that's kind of an example that we have been kind of trying to solve such a repeated root case. Okay, so now if you look at the solution, okay, so if you look at this solution, okay, so you look at the solution, you can write a solution in terms of components. Okay, so in terms of components, the x1 of t is going to be c1 e to the power of 2t plus c2t times e to the power of 2t, and x2 of t is going to be c1 minus c1 e to the power of 2t minus c2t power of 2t and minus e to the power of 2t. Okay, so if you draw trajectories of the solution, okay, so like what we did last time, you just plot the trajectory as t changes of the solution. You're going to have such a picture. In this case, we're going to call it origin O an improper node point. Why is it called improper node point? Remember, the node point means that eigenvalues are of the same sign, right? So here, both the eigenvalues are the same. They're both equal to 2, so you're going to have a node point. But why it's improper? Because the improperness is caused by the fact that you're going to have some kind of twisting by the t here, right? So these t's are results of the golden principle that will create improperness because the solution is not going to be like directly going out of the zero, like something like this, but rather it's going to kind of rotate a little bit until you reach like the heat out of the zero. Is that going to happen? Okay, so that's going to be like what you have for the correspondency of last lecture. Okay, so now let us try to practice. Okay, so let us try to practice one more example. Okay, so let us try to practice like one more example and see what we're going to have here. Okay, so let us try to practice one more example and see what we're going to have here. Okay, so in this case you are going to solve. Okay, so in this problem it's going to ask you to solve this system, right? So you solve such a system. Okay, so now how are you going to solve such a system? Okay, so that means, okay, so let's say, okay, so let me make it larger. Okay, so we are going to solve such a system. Okay, so how are we going to do that? Well, the method is the same. So that means you're going to set the matrix A is equal to 6 minus 4, 1, and 2, right? So that's going to be your matrix A. So then you're going to solve for the eigenvalues. Determinant of A minus Ri is going to be the determinant of 6 minus R minus 4 and 1 and 2 minus R, right? So that's going to give you like R minus 6 multiplied by R minus 2 and plus the 4. So that's going to be R squared minus the 8 times R plus the 12 plus 4 plus the 16. So this is minus R minus 4 squared. You're going to set to be 0. Is that good, family? Now from this equation, it means that you solve for the roots R1 is equal to R2 is equal to 4. They are the common real eigenvalues. Is that good, family? Okay. As long as you have these eigenvalues, you start to look for eigenvectors, right? So that means you're going to look for AX is equal to 4 times X. So that's going to give you the equation, which is like 0 minus 4, 1, and 2 multiplied by X1 and X2 is equal to 4 times the X1 and X2, right? So it's 4 times X1, X2. So that's going to give you 6 times X1 minus 4 times X2 is equal to 4 times X1, as well as the equation X1 plus 2 times X2 is equal to 4 times X2. So you get this equation. Now it's going to give you the solution. Solution is going to be like 2 times X1 is equal to 4 times X2, first equation. Second equation is going to be like X1 is equal to 2 times X2. So they are actually equivalent equations, which is not surprise, which is a good answer. So that means that you're going to find your X. X is equal to X2 is 1, X1 is 2. Because X1 is 2, X2. Is a good fair. You want integers, right? So you don't want like 1, 1/2, although it's correct, but it's not what you want because it doesn't have, it has something that's irrational, right? You want integers. So that's your first vector X. Now, given that first vector X, you're going to look for Y, right? So the Y is going to satisfy this A minus Ri. Okay, so but R is equal to 4. The eigenvalue is 4. So A minus 4I of the Y is equal to X. Is that good, family? Okay, so that means you want to look for A minus 4I, which is the matrix 6 minus 4, 1 and 2 minus 4 times the 1, 0, 0, 1. So that's going to be like 6 minus 4 is 2, minus 4 and 1, right? So and 2 minus the 4 is minus 2. So you're going to have this. Is that good, family? Okay, so that means 2 minus 4, 1 minus 2. Okay, so multiplied by y1 and y2 is going to be equal to the vector 2 and 1. So that's going to have this equation 2y1 minus 4 times y2 is equal to 2, and y1 minus 2 times y2 is equal to 1. Is that good, family? Okay, so you can, but these two equations are of course equivalent. Because if you multiply the second equation by 2, you get the first equation. Is that good for everybody? Okay, so that means you can set y1 and y2. Okay, so the vector to be equal to what? Well, you can set the vector with the components y1, y2, which is nothing but your vector y, right? So which is nothing but your vector y. So if I set y2 to be 0, then the y1 can be equal to 1. So that's going to be a solution. Is that good for everybody? Right? So that's going to be a solution to your original problem, right? So the y. So once you have the both in x and y, right? So you get a general solution. Okay, so you get a general solution, right? So you get a general solution to the problem is going to be given by x of t is c1 e to the power of 4t multiplied by x, right? So what is x? Well, x is equal to 2 and 1. So that means the x is equal to 2 and 1 plus c2. Okay, so according to our formula, it should first do the golden principle as before, right? So t e power 4t, and then it's going to be e power 40. There is no t here, e power 40, but multiplied by the second vector, right? The vector is 1 and 0, so you're going to have 1, 0. That's going to be like the general solution. Is that good for everybody? Okay. Remember, the C2 works for both of these last two terms. There is no C3. Okay, so the C2 is just works for the sum of these two terms, and C1 works for the original term. Is that good for everybody? Okay, so therefore, we're going to look for a particular solution. So remember, the initial condition says that x of 0 is 1, 1. So that means you're going to set x of 0. So that's going to be C1 multiplied by 2, 1 plus C2 multiplied by, when t is 0, you don't have this term. So that's when t is 0, this is 1. So that's 1, 0. So this is going to be like 2C1 plus C2 and C1. Okay, so 2C1 plus C2 and C1. So this is going to be give you the solution is equal to 1, 1, right? So it's equal to 1, 1. So that means 2C1 plus C2 is equal to 1 and C1 is equal to 1. So that's going to give you like C1 is equal to 1. C2 is going to be equal to, so minus 1, because 2C1 is 2. C2 is minus 1, so you get two solutions. So that means you indeed found a particular solution. Okay, so indeed you find a particular solution which is given by x of t is going to be equal to e to the power of 4t multiplied by 2 and 1, right? So plus this C2 is minus sign, so that's going to be minus. Okay, so minus the t e to the power of 4t multiplied by 2 and 1 plus e to the power of 4t multiplied by 1, 0. So that's going to be like the particular solution to this problem. Okay, so that's going to be like the particular solution to this problem. Okay, so that's going to be like the particular solution to this problem. Right, so you find this particular solution. Now, if you want the solution to be in the components, you can actually write it in the components. So that's going to be like 2 times e power 4t minus 2t e power 4t plus e power 4t. So the first component. Second component is e power of 4t minus t times e power of 4t, and that's the first and second components. Is that good for everybody? Right? So that's going to be the first and second components. Okay, so that's going to be like what we have for this example. Okay, so that's what we have for this example. So as a summary, today's lecture. Okay, so as a summary, today's lecture we have considered the real repeated root case. Okay, so we have considered the real repeated root case. So that kind of resolves this question, right? So if you have a real repeated roots, then what's going to happen for the solution system, to the system of linear equations? Okay. So next time we're going to kind of consider the real complex conjugate root case. Okay. So that means the first and second solution are conjugate to each other, and then we're going to try to understand what will be the solution. Okay. So that will be the material. Okay. So that will be the material for our next lecture. Okay, so that's maybe all I want to say for today's lecture, and let's stop here, and I'll see you in the next lecture. Okay, so see you in the next lecture.